Okay, hello everyone, and I'm a bit late today. I have started like a couple hours ago, but I did not record anything. I was just doing some editing to the previous videos, so it's make no sense to record myself. I'm editing the video I recorded last night, so yeah, but it's take long. You can even look here which one. It's still like 26% of editing. Still waiting. And yeah, 27th February. Okay. So we stopped yesterday on Zeus 3.
Lindor. Darujte jedinečnou chvilku s novinkou Lindor malý
I don't know why my laptop is so slow today.
(1943) Colossus, World War II cryptography.
So the first machine that was built to do this was called the Heath Robinson. It was named after this British cartoonist who drew cartoons of crazy machines to do operations. This one was for peeling potatoes. And the timeline of this is quite interesting. So the first operator mistake, the retransmission with abbreviations, happened in August 1941. That was intercepted. Over the next year, that was enough to learn from the two intercepted messages the structure of the machine, then to understand it well enough to develop this technique, the double delta technique, for finding the correct configuration and to break messages. By December 1942, they decided to build a machine and put the resources necessary to design and build a machine. It was requested to be done by June of 1943. It was actually delivered 3 months early. By April 1943, they had the first machine delivered and operational, and it could process messages about 2,000 characters per second. So it was able to do 7 XOR operations in half a millisecond, running this paper tape through at 20 kilometers per hour. This was not quite fast enough. A lot of the value in decrypting messages, especially in wartime, is being able to decrypt them before what the message is describing actually happened. So they built a faster machine. And the faster machine was called Colossus. This was operational by January 1944. And the big change that made Colossus much faster and more useful than the Heath Robinson machines was that they replaced the configurations which were previously on a tape with an electronic key text generator. The logic is doing all the XORs and counting the number that are 0. And then it's printing out those tallies so you can go back and find the right configuration. And the ciphertext is still on a paper tape. This is spinning through about 50 kilometers an hour. This is a pretty impressive sight when it was operating, processing 5,000 characters per second. And what made this arguably the first computer was because of the electronic key text, this logic was a little bit programmable. It didn't do always exactly the same thing. There were ways to program it to do slightly different operations depending on what the analyst thought was the most useful thing to do with that intercepted ciphertext. So this was arguably the first programmable digital electronic computer. It wasn't fully programmable. It wasn't a general purpose computer, but it could be programmed to change its behavior slightly. You can see what this looked like during World War II. There are very few pictures of it. This was a very secretive operation. And the machines were actually all destroyed after the war. A lot of the value in breaking a cipher is to make sure that no one else knows that you've broken it. This is different from academic cryptography, where people like to publicize when they break ciphers. In military cryptography, the whole value of breaking a cipher is that your enemy keeps using it. So you want to keep it very secretive that you've done that. A lot of the work on Colossus was not declassified until the mid-90s. Today, if you visit Bletchley Park, you can see a replica, a rebuilt version of Colossus. This is my picture of it from 2004. It does look very similar to the black and white picture from World War II. Unfortunately, they don't operate it frequently, so you won't get to see the tape spinning through at 50 kilometers an hour and all the crunching going on, unless you're very lucky to go one of the few days a year that they might actually operate it. So these Colossus machines had a huge impact on World War II. By the end of the war, there were 10 of them continuously operating at Bletchley Park, decrypting all the traffic that they could intercept. They decoded over 63 million letters of messages in Axis communications. Among the things they learned from them were the troop locations of the Axis on D-Day. This was very helpful for planning the operation. So why did I tell you this story? Well, first of all, it is an important story in the history of both the world as well as computing. But this isn't meant to be a history class, although I certainly like to have historical excursions when I can. But it's also very relevant to modern cryptanalysis. Modern ciphers are much better than the Lorenz cipher. And the main reason for that is we can use computing power to do the encryption. But the basic ideas are actually quite similar. So the goal of the cipher is to hide all the statistical properties that are inherent in the message. And they're present in the key, at least the generated key. The actual key, we hope, is perfectly random. Finding perfect randomness and getting it in computing is quite challenging. But let's assume we have a perfectly random key. What we learned from the perfect cipher analysis is that the key must be shorter than the message. That means in order for the cipher to work, we need to generate more key bits than we actually have. And so even if the original key, and you can think of that in the case of Colossus as the configuration of the machine that comes from some codebook that could be perfectly randomly generated and shared between the endpoints, that is only the starting configuration. There's some larger key that has to be generated to produce the ciphertext. And so both the key and the message have some statistical properties. The goal of the cipher is to hide all those properties. The goal of the analyst is to find statistical properties in the ciphertext and then to use those to break the key or the message. In the case of Bletchley Park breaking the Lorenz cipher, they found the statistical properties when you looked across channels at subsequent letters. There were some statistical properties that were not hidden by the cipher. And that was because of a mechanical weakness, that all the S wheels either all moved or didn't move. And that meant that instead of having the long period with no repetition of 19 million letters that the users of the Lorenz machine thought it had, the Allies could break that down and find a pattern that was only 1,271 letters long with much fewer configurations to try to have a good guess if the cipher with many fewer guesses needed. In a modern cipher, we think of that as a mathematical weakness. There's some problem in the mathematics of the cipher that leaves some statistical property that a cryptanalyst could exploit. The other relevance to modern cryptanalysis is it's really lots of hard work to do that. I find it quite amazing what Bletchley Park was able to do with Colossus. It still took 6 months of effort looking at those two messages to figure out the key and interpret the key structure from that. That requires an awful lot of trial and error and a lot of creativity, but also a lot of tedious work. In modern cryptanalysis, we try to do as much of the tedious work as possible by computers, but there's still lots of hard work that goes into breaking a cipher. And motivation certainly helps a lot for that. In the case of Bletchley Park, the fear that your country was under attack is a pretty strong motivation. So we won't talk in much detail about modern symmetric ciphers in this course. There's a couple of reasons for this.
Introducing Remarkable Paper Pro, the ultimate paper tablet.
Simply have not learned. Is codifying that small observation. It says that a linear combination of linear combinations is a linear. Hi, hello, hi. So last time we finished the first chapter, and one of the lessons of the first chapter was that we are studying linear combinations. When we're talking about solving linear systems, we're really talking about taking linear combinations of the rows. We're studying linear combinations. So in this chapter, we want to expand what linear combinations are about, so that today's check-in is that first step in that direction. Here I have a linear combination of three vectors. Not a linear combination of numbers like we saw in a lot of the previous chapter, but a linear combination of three vectors. We've already seen some of this when we wrote the solution sets of linear systems and when we wrote the equations of planes, but nonetheless I'm making it explicit here. This is a linear combination of three vectors and we're asked to solve it. So we're thinking about what can happen when you try to do equations involving these objects. Okay, so let's write it down. So I want to take the linear combination of those three vectors, and so I have, just to start in here, I have 1, 2, 0 times x, 1, 1 minus 1 times y, and 0, 3, 0 times z equals 0, 0, 0. I like the 0, 0, 0, the homogeneous case, for reasons that we'll see later on today. And I want to figure out what x, what y, what z makes this true. So this is just like when you had numbers, except now it's letters. And of course, we've seen this already, but I'm trying to bring out a fact that we're taking linear combinations of things other than numbers. Okay, so of course, a person thinks to look at the first line and get, let's see, x plus y equals 0. The second line gives you 2x plus y plus 3z equals 0. And the third line gives you minus y equals 0. And these zeros over here means that you cannot have a contradictory equation. So you've either got one solution or infinitely many solutions. I don't know, I'm not going to actually solve it because watching me do arithmetic is not very interesting. So the point though is that off we go. Gauss's method gets us an answer. That's all we need to know, is that we can solve that, and then off we go. Okay, next up though, I want to underline the same thing here, is that we can take linear combinations of things other than numbers. So here I am taking a linear combination of matrices and asking basically the same question, is can you give me a solution, an x, a y, and a z, that makes this particular linear combination equation true? And of course, for number 2, of course, it's exactly the same idea. The point was to illustrate that I can take linear combinations of things other than numbers in some reasonable way. All right, so just to illustrate here, I get the system 2x plus y.
This college algebra course is different than other college algebra courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, the instructor, Ed Protowski, will also show you how to implement all the concepts in Python. This course is for everybody, but especially those interested in computer science.
Hello, and welcome to the Algebra with Python course. My name is Ed, and I'll be your guide on this adventure. So we're going to learn about algebra and how to write Python code to do all of your algebra. Because there's so many different things that you can do with formulas. You know, you learn these formulas. Hey, anytime you have a formula, you can write code to use it. So that's what we're going to do. We're going to write some code using the Google Colab notebook, and that's Python.
Which European countries have the lowest taxes for investors?
Okay, so you're an expat or nomad here in Europe and you want to start investing. Maybe you've read about how if you bought $10,000 of Amazon stock 20 years ago, today that would be worth $1 million. Or you've heard about the FIRE movement, financial independence, retire early, where many expats in different professions such as teachers, designers, programmers invest their money and escape their 9 to 5 and retire at 40 or
Back to basics. So from not Friday, Saturday, I'll try to finish this chapter, which is the basic. It's just a recap, like it isn't really to learn it by heart, but just to remember the things. If I missed something, if I don't memorize anything, I might just remember it. Yeah, so this is a nice book as well. Thank you. I will get back to these people. I mean, I might skip them now, but oh my god, the laptop he's so slow. Like I can't done the things in this way. One of the reason actually it's the screen recording. Like you can see even I mean I'm really gonna study all that. I don't know what's happened today. It's really so slow. Like it will take all the day just to download something, attach something. It's like 2 second process. It's take 1 hour.
But I could say 2/4, I can call it a fraction, but it's also a ratio. And then a proportion is two equal ratios. So if I know that these are equal, then there's other things I can do with this. And one of the things that works and becomes very useful is cross multiplying. So if these two are equal ratios, then I can cross multiply the diagonals. I can do 2 times 10 equals 4 times 5. And that's another way to write this, so then I can get it out of the proportion mode, and I can use this to double check, or I can solve for things. So 2 times 10, we see 20 equals 20, and then that's true. So, we confirm that that works. We can always do this. If these were other numbers, I can check to see if this really is true, cross multiplying, because if that doesn't work, then that wouldn't be true. And I can also use it if one of these numbers is unknown. So if I have 3 out of 6 equals x out of 4. Now, there's other ways to solve this, but this is the go-to way because it works every time. So when I do my cross multiplying, then I can do this. 3 times 4 is 12 equals 6x. So there we go. 3 times 4 is 12, and then 6 times x is 6x. And then I know that the next step I'm going to do is going to be dividing by 6. So then I get that x equals 2. Now, in doing that, we can jump ahead and say, okay, I know that when I'm, so x would be,
I don't like writing essays, but here are my marks for them. So bestie, I'm going to tell it to you straight. Personally, I prefer using Grammarly when it comes to writing.
This college algebra course is different than other college algebra courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, the instructor, Ed Protowski, will also show you how to implement all the concepts in Python. This course
Ready to learn mathematics behind machine learning, generative AI, or cutting-edge tech? Then you are in the right place. Today we are going to learn linear algebra like never before. In this crash course, in 6 hours, we are going to learn the basics and the fundamental concepts in linear algebra, a fundamental part in mathematics when it comes to many applied sciences. Our crash course in Fundamentals to Linear Algebra will be a great starting point for anyone
Okay, I might.
One who wants to refresh their linear algebra and see from
Co tyhle?
Dobrý.
A tyhle?
Taky dobrý.
Ready to learn mathematics behind machine learning, generative AI?
This college algebra course is different than other college algebra courses. Like many other ones, you will
simply have not learned linear algebra. You can't watch videos. That's all there is to it. It's like learning to play a violin. You can't learn to play a violin solely by watching other people play violins. That's just not how it happens. Okay. Okay, enough finger wagging. Nice to meet you, and I hope that you enjoy the videos. Hope you find them useful. So next up will be solving linear systems part 1. Very good. Hello. Hello. I'm Jim.
This college algebra course is different than other college algebra courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, the instructor, Ed Protowski, will also show you how to implement all the concepts in This college algebra course is different than other college algebra courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, the instructor
simply have not learned linear algebra. You can't watch videos. That's all there is to it. It's like learning to play a violin. You can't learn to play a violin solely by watching other people play violins. That's just not how it happens. Okay. Okay, enough finger wagging. Nice to meet you, and I hope that you enjoy the videos. Hope you find them useful.
Let's see what he's gonna do.
Řeči, řeči, řeči. Diskuse je důležitá. To by stačilo. Někdo musí něco udělat. Jeden solární panel? Opravdu? Měli byste udělat celou čtvrť. Není na čase, aby s tím konečně někdo něco...
Hej, my už to řešíme. Nedělejte si starosti.
Nechte to na nás. Postaráme se, aby nová energie měla skutečně smysl. E.ON.
Objevte Sajos Brow Tint pro perfektní obočí jako ze salonu z pohodlí domova. Sajos.
This college algebra course is different than other college algebra courses. Like many other ones, you will be learning all the concepts from an experienced university professor.
This roadmap will still be adjustable. Just like I will take it as a base for me, I will go through it day by day. Maybe it will be extended, maybe other way around. Final 2 weeks, deep dive into proofs, work in additional problem and solution manuals, explore complete. Let's see, but like okay, so what is math now? Linear algebra. I mean, these things actually, it's really make change. So it's just will be a nice base.
We're here on a runway because for some reason Brady has printed out the first 1 million digits of pi on a continuous mile-long piece of paper, which we are going to very carefully unravel today and go for a tour of 1 million digits of pi.
All around us.
The beginning of mathematics starts with numbers and counting, which at one time humans did not know anything about. One of the age-old questions actually is, did we invent numbers or were they already there? Now of course we use a 10-digit number system, but there's no mathematical reason for that. There's no reason we could not have 9 digits, which means after 8 the next number would be 10 because you'd be out of digits and you would need to reset the ones place to 0 and then add a 1. This would represent what we know of as 9 if there were 9 digits.
The world is made up of patterns and sequences. They're all around us. Day becomes night. Animals travel across the earth in ever-changing formations. Landscapes are constantly altering. One of the reasons mathematics began was because we needed to find a way of making sense of these natural patterns. The most basic concept, our world is made up of patterns and sequences. They're all around us. Day becomes night. Animals travel across the earth in ever-changing formations. Landscapes are constantly altering. One of the reasons mathematics began was because we needed to find a way of making sense of these natural patterns. The most basic concepts of maths, space and quantity, are hardwired into our brains. Even animals have a sense of distance and number, assessing when their pack is outnumbered and whether to fight or fly, calculating whether their prey is within striking distance. Understanding maths is the difference between life and death.
But it was man who took these basic concepts and started to build upon these foundations. At some point, humans started to spot patterns, to make connections, to count, and to order the world around them. And with this, a whole new mathematical universe began to emerge.
This is the River Nile. It's been the lifeline of Egypt for millennia. I've come here because it's where some of the first signs of mathematics as we know it today emerged. People abandoned nomadic life and began settling here as early as 6000 BC. The conditions were perfect for farming.
The most important event for Egyptian agriculture each year was the flooding of the Nile. So this was used as a marker to start each new year. Egyptians did record what was going on over periods of time. So in order to establish a calendar like this, you need to count how many days, for example, happened in between lunar phases, or how many days happened in between two floodings of the Nile.
Recording the patterns of the seasons was essential not only to their management of the land, but also their religion. The ancient Egyptians who settled on the Nile banks believed it was the river god Hapi who flooded the river each year. And in return for the life-giving water, the citizens offered a portion of the yield as a thanksgiving.
As settlements grew larger, it became necessary to find ways to administer them. Areas of land needed to be calculated, crop yields predicted, taxes charged and collated. In short, people needed to count and measure.
The Egyptians used their bodies to measure the world, and it's how their units of measurement evolved. A palm was the width of a hand, a cubit an arm length from elbow to fingertips. Land cubits, strips of land measuring a cubit by 100, were used by the pharaoh's surveyors to calculate areas.
There's a very strong link between bureaucracy and the development of mathematics in ancient Egypt. And we can see this link right from the beginning, from the invention of the number system, throughout Egyptian history, really. For the Old Kingdom, the only evidence we have are metrological systems, that is, measurements. And the development of mathematics in ancient Egypt. And we can see this link right from the beginning, from the invention of the number system, throughout Egyptian history, really. For the Old Kingdom, the only evidence we have are metrological systems, that is, measurements for areas, for length. This points to a bureaucratic need to develop such things.
It was vital to know the area of a farmer's land, so he could be taxed accordingly. Or if the Nile robbed him of part of his land, so he could request a rebate. It meant that the pharaoh's surveyors were often calculating the area of irregular parcels of land. And it was the need to solve such practical problems that made them the earliest mathematical innovators. The Egyptians needed some way to record the results of their calculations. Amongst all the hieroglyphs that cover the tourist souvenirs scattered around the city of Cairo, I was on the hunt for those that recorded some of the first numbers in history. They were difficult to track down. But I did find them in the end. The Egyptians were using a decimal system, motivated by the 10 fingers on our hands. The sign for 1 was a stroke, 10 a heel bone, 100 a coil of rope, and 1,000 a lotus plant.
Yeah, how much is this t-shirt? 25. Yes. So that would be 2 knee bones and 5 strokes. Yes. So you're not going to charge me anything up here?
Here, 1 million.
1 million?
Oh my God.
No.
Is this 1 million?
1 million. Yeah, that's pretty big.
The hieroglyphs are beautiful, but the Egyptian number system was fundamentally flawed. They had no concept of a place value. So 1 stroke could only represent 1 unit, not 100 or 1,000. Although you can write 1,000,000 with just 1 character, rather than the 7 that we use, if you want to write 1,000,000 minus 1, then the poor old Egyptian scribe has got to write 9 strokes, 9 heel bones, 9 coils of rope, and so on, a total of 54 characters. Despite the drawback of this number system, the Egyptians were brilliant problem solvers.
We know this because of the few records that have survived. The Egyptian scribes used sheets of papyrus to record their mathematical discoveries. This delicate material made from reeds decayed over time, and many secrets perished with it. But there's one revealing document that has survived.
The Rhind mathematical papyrus is the most important document we have today for Egyptian mathematics. We get a good overview of what types of problems the Egyptians would have dealt with in their mathematics. We also get explicitly stated how multiplications and divisions were carried out.
The papyri show how to multiply 2 large numbers together. But to illustrate the method, let's take 2 smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in 1 column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 would become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12, he adds those together to get the answer of 18. But for me, the most striking thing about this method is that the scribe has effectively written that second number in binary. 6 the powers of 2.
Chuť na všechno, co tě baví. Corny Protein.
Sprchový gel Old Spice 3 v 1. Vůně parfémové kvality.
Multiply two large numbers together. But to illustrate the method, let's take two smaller numbers. Let's do 3 times 6. The scribe would take the first number 3 and put it in one column. In the second column, he would place the number 1. Then he would double the numbers in each column. So 3 becomes 6, and 6 would become 12. And then in the second column, 1 would become 2, and 2 becomes 4. Now here's the really clever bit. The scribe wants to multiply 3 by 6. So he takes the powers of 2 in the second column, which add up to 6. So that's 2 plus 4. Then he moves back to the first column and just takes those rows corresponding to the 2 and the 4. So that's 6 and the 12. He adds those together to get the answer of 18. But for me, the most striking world depends on the same principles that were used in ancient Egypt.
The Rhind Papyrus was recorded by a scribe called Ahmes around 1650 BC, and its problems are concerned with finding solutions to everyday situations. Several of the problems mention bread and beer, which isn't surprising as Egyptian workers were paid in food and drink. One is concerned with how to divide 9 loaves equally between 10 people without a fight breaking out.
I've got 9 loaves of bread here. I'm going to take 5 of them and cut them into halves.
Of course, 9 people could shave a 10th off their loaf and give the pile of crumbs to the 10th person. But the Egyptians developed a far more elegant solution.
Take the next 4 and divide those into thirds. But 2 of the thirds I'm now going to cut into fifths, so each piece will be 1/15. Each person then gets 1/2, and 1/3, and 1/15. It's through such seemingly practical problems that we start to see a more abstract mathematics developing. Suddenly new numbers are on the scene, fractions, and it isn't too long before the Egyptians are exploring the mathematics of these numbers.
Fractions are clearly of practical importance to anyone dividing quantities for trade in the market. To log these transactions, the Egyptians developed notation which recorded these new numbers. One of the earliest representations of these fractions came from a hieroglyph which had great mystical significance. It's called the Eye of Horus. Horus was an Old Kingdom god, depicted as half man, half falcon.
According to legend, Horus's father was killed by his other son, Seth. Horus was determined to avenge the murder. During one particularly fierce battle, Seth ripped out Horus's eye, tore it up, and scattered it over Egypt. But the gods were looking favorably on Horus. They gathered up the scattered pieces and reassembled the eye.
Co tam děláte? Chceme se dostat do Dánska.
Kup alespoň 2 sušenky Opavia a zapoj se do soutěže o zájezd do Dánska. A když správně odpovíš na otázku, zvýšíš svoje šance.
Each part of the eye represented a different fraction, each one half the fraction before. Although the original eye represented a whole unit, the reassembled eye is 1/64 short.
Although the Egyptians stopped at 1/64, implicit in this picture is the possibility of adding more fractions, halving them each time, the sum getting closer and closer to 1, but never quite reaching it. This is the first hint of something called a geometric series, and it appears at a number of points in the Rhind Papyrus. But the concept of infinite series would remain hidden until the mathematicians of Asia discovered it centuries later. Having worked out a system of numbers, including these new fractions, it was time for the Egyptians to apply their knowledge to understanding shapes that they encountered day to day. These shapes were rarely regular squares or rectangles, and in the Rhind Papyrus we find the area of a more organic form, the circle.
What is astounding in the calculation of the area of a circle is its exactness, really. How they would have found their method is open to speculation, because the texts we have do not show us the methods how they were found.
This calculation is particularly striking because it depends on seeing how the shape of the circle can be approximated by shapes that the Egyptians already understood. The Rhind Papyrus states that a circular field with a diameter of 9 units is close in area to a square with sides of 8. But how would this relationship have been discovered? My favourite theory sees the answer in the ancient game of Mancala. Mancala boards were found carved on the roofs of temples. Each player starts with an equal number of stones, and the object of the game is to move them around the board, capturing your opponent's counters on the way.
As the players sat around waiting to make their next move, perhaps one of them realised that sometimes the balls fill the circular holes of the Mancala board in a rather nice way. He might have gone on to experiment with trying to make larger circles.
Perhaps he noticed that 64 stones, the square of 8, can be used to make a circle with diameter 9 stones. By rearranging the stones, the circle has been approximated by a square. And because the area of a circle is pi times the radius squared, the Egyptian calculation gives us the first accurate value for pi.
The area of the circle is 64. Divide this by the radius squared, in this case 4.5 squared, and you get a value for pi. So 64 divided by 4.5 squared is 3.16, just a little under 2/100ths away from its true value. But the really brilliant thing is the Egyptians are using these smaller shapes to capture the larger shape.
But there's one imposing and majestic symbol of Egyptian mathematics we haven't attempted to unravel yet: the pyramid. I've seen so many pictures that I couldn't believe I'd be impressed by them. But meeting them face to face, you understand why they're called one of the 7 wonders of the ancient world. They're simply breathtaking. And how much more impressive they must have been in their day, when the sides were as smooth as glass, reflecting the desert sun.
To me, it looks like there might be mirror pyramids hiding underneath the desert, which will complete these shapes to make perfectly symmetrical octahedrons. Sometimes, in the shimmer of the desert heat, you can almost see these shapes.
It's the hint of symmetry hidden inside these shapes that makes them so impressive for a mathematician. The pyramids are just a little short to create these perfect shapes. But some have suggested that another important mathematical concept might be hidden inside the proportions of the Great Pyramid: the golden ratio. 2 lengths are in the golden ratio if the relationship of the longest to the shortest is the same as the sum of the 2 to the longest side. Such a ratio has been associated with the perfect proportions one finds all over the natural world, as well as in the work of artists, architects, and designers for millennia. Whether the architects of the pyramids were conscious of this important mathematical idea, or were instinctively drawn to it because of its satisfying aesthetic properties, we'll never know. For me, the most impressive thing about the pyramids is the mathematical brilliance that went into making them, including the first inkling of one of the great theorems of the ancient world, Pythagoras' theorem.
In order to get perfect right-angled corners on their buildings and pyramids, the Egyptians would have used a rope with knots tied in it. At some point, the Egyptians realised that if they took a triangle with sides marked with 3 knots, 4 knots and 5 knots, it guaranteed them a perfect right angle. This is because 3 squared plus 4 squared is equal to 5 squared. So we've got a perfect Pythagorean triangle. In fact, any triangle whose sides satisfy this relationship will give me a 90-degree angle. But I'm pretty sure that the Egyptians hadn't got this sweeping generalization of their 3-4-5 triangle.
We would not expect to find a general proof because this is not the style of Egyptian mathematics. Every problem was solved using concrete numbers, and then if a verification would be carried out at the end, it would use the result and these concrete given numbers. There's no general proof within the Egyptian mathematical texts.
It would be some 2,000 years before the Greeks and Pythagoras would prove that all right-angled triangles shared certain properties. This wasn't the only mathematical idea that the Egyptians would anticipate. In a 4,000-year-old document called the Moscow Papyrus, we find a formula for the volume of a pyramid with its peak sliced off, which shows the first hint of calculus at work.
For a culture like Egypt that is famous for its pyramids, you would expect problems like this to have been a regular feature within their mathematical texts. The calculation of the volume of a truncated pyramid is one of the most advanced bits, according to our modern standards of mathematics, that we have from ancient Egypt.
The architects and engineers would certainly have wanted such a formula to calculate the amount of materials required to build it. But it's a mark of the sophistication of Egyptian mathematics that they were able to produce such a beautiful method. To understand how they derived their formula, start with a pyramid built such that the highest point sits directly over one corner. 3 of these can be put together to make a rectangular box. So the volume of the skewed pyramid is 1/3 the volume of the box. That is, the height times the length times the width divided by 3.
Now comes an argument which shows the very first hints of the calculus at work, thousands of years before Gottfried Leibniz and Isaac Newton would come up with the theory.
Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid to make the could cut the pyramid.
Isaac Newton would come up with the theory.
Suppose you could cut the pyramid into slices. You could then slide the layers across to make the more symmetrical pyramid you see in Giza. However, the volume of the pyramid has not changed, despite the rearrangement of the layers. So the same formula works. The Egyptians were amazing innovators, and their ability to generate new mathematics was staggering. For me, they revealed the power of geometry and numbers, and made the first moves towards some of the exciting mathematical discoveries to come. But there was another civilization that had mathematics to rival that of Egypt, and we know much more about their achievements. This is Damascus, over 5,000 years old and still vibrant and bustling today. It used to be the most important point on the trade routes linking old Mesopotamia with Egypt. The Babylonians controlled much of modern-day Iraq, Iran and Syria from 1800 BC. In order to expand and run their empire, they became masters of managing and manipulating numbers.
It's 9:15. How am I already underwater?
I'm in the same boat. I'm in an actual boat.
I thought Grammarly just...
We have...
They became masters. The Babylonians controlled much of modern-day Iraq, Iran and Syria from 1800 BC. In order to expand and run their empire, they became masters of managing and manipulating numbers.
We have law codes, for instance, that tell us about the way society is ordered. Now, the people we know most about are the scribes, the professionally literate and numerate people who kept the records for the wealthy families and for the temples and palaces.
scribe schools existed from around 2500 BC. Aspiring scribes were sent there as children and learned how to read, write, and work with numbers. Scribe records were kept on clay tablets, which allowed the Babylonians to manage and advance their empire. However, many of the tablets we have today aren't official documents, but children's exercises. It's these unlikely relics that give us a rare insight into how the Babylonians approached mathematics.
So this is a geometrical textbook from about the 18th century BC, and I hope you can see that there are lots of pictures on it, and underneath each picture is a text that sets a problem about the picture. So, for instance, this one here says, I drew a square 60 units long, and inside it I drew 4 circles. What are their areas? So this little tablet here was written 1,000 years at least later than the tablet here, but it has a very interesting relationship to it. It also has 4 circles on in a square, roughly drawn, but this isn't a textbook, it's a school exercise, so that the adult scribe who's teaching the student is being given this as an example of completed homework or something like that.
Like the Egyptians, the Babylonians appeared interested in solving practical problems to do with measuring and weighing. The Babylonian solutions to these problems are written like mathematical recipes. A scribe would simply follow and record a set of instructions to get a result. Here's an example of a kind of problem they'd solve. Now I've got a bundle of cinnamon sticks here, but I'm not going to weigh them. Instead, I'm going to take 4 times their weight and add them to the scales. Now I'm going to add 20 jinn. Jinn was the ancient Babylonian measure of weight. I'm going to take half of everything here and add it again. So that's 2 bundles and 10 jinn. Now everything on this side is equal to 1 manna. 1 manna was 60 jinn. And here we have one of the first mathematical equations in history. Everything on this side is equal to 1 manna. But how much does the bundle of cinnamon sticks weigh? Without any algebraic language, they were able to manipulate the quantities to be able to prove that the cinnamon sticks weighed 5 jinn. In my mind, it's this kind of problem which gives mathematics a bit of a bad name. You can blame those ancient Babylonians for all those tortuous problems you had at school. But the ancient Babylonian scribes excelled at this kind of problem. Intriguingly, they weren't using powers of 10 like the Egyptians. They were using powers of 60. The Babylonians invented their number system, like the Egyptians, by using their fingers. But instead of counting through the 10 fingers on their hand, Babylonians found a much more intriguing way to count body parts. They used the 12 knuckles on one hand and the 5 fingers on the other to be able to count 12 times 5, i.e. 60 different numbers. So for example, this number would have been 2 lots of 12, 24, and then 1, 2, 3, 4, 5 to make 29. But the number 60 had another powerful property. It can be perfectly divided in a multitude of ways. Here are 60 beans. In a multitude, 60 had another powerful property. It can be perfectly divided in a multitude of ways. Here are 60 beans. I can arrange them in 2 rows of 30. 3 rows of 20. 4 rows of 15. 5 rows of 12. Or 6 rows of 10. The divisibility of 60 makes it a perfect base in which to do arithmetic. The base 60 system was so successful
we still use elements of it today. Every time we want to tell the time, we recognize units of 60, 60 seconds in a minute, 60 minutes in an hour. But the most important feature of the Babylonians' number system was that it recognized place value. Just as our decimal numbers count how many lots of tens, hundreds and thousands you're recording, the position of each Babylonian number records the power of 60 you're counting.
Instead of inventing new symbols for bigger and bigger numbers, they would write 111, so this number would be 3,661. The catalyst for this discovery was the Babylonians' desire to chart the course of the night sky.
The Babylonians' calendar was based on the cycles of the moon, and so they needed a way of recording astronomically large numbers. Month by month, year by year, these cycles were recorded. From about 800 BC,
Come on, dig deep now. You love it, Reese. We love it. Come on. Yes, Reese.
If you're trading for the flashy lifestyle, you're going to fail. The truth is, you're not going to be able to.
There were complete lists of lunar eclipses.
The Babylonian system of measurement was quite sophisticated at that time. They had a system of angular measurement, 360 degrees in a full circle. Each degree was divided into 60 minutes. A minute was further divided into 60 seconds. So they had a regular system for measurement, and it was in perfect harmony with their number system. So it was well suited not only for observation, but also for calculation.
But in order to calculate and cope with these large numbers, the Babylonians needed to invent a new symbol. And in so doing, they prepared the ground for one of the great breakthroughs in the history of mathematics: zero.
In the early days, the Babylonians, in order to mark an empty place in the middle of a number, would simply leave a blank space. So they needed a way of representing nothing in the middle of a number. So they used a sign as a sort of breathing mark or a punctuation mark, and it comes to mean zero in the middle of a number.
This was the first time zero in any form had appeared in the mathematical universe. But it'd be over 1,000 years before this little placeholder would become a number in its own right. Having established such a sophisticated system of numbers, they harnessed it to tame the arid and inhospitable land that ran through Mesopotamia. Babylonian engineers and surveyors found ingenious ways of accessing water and channeling it to the crop fields. Yet again, they used mathematics to come up with solutions. The Orontes Valley in Syria is still an agricultural hub, and the old methods of irrigation are being exploited today just as they were thousands of years ago. Many of the problems in Babylonian mathematics are concerned with measuring land. And it's here we see for the first time the use of quadratic equations, one of the greatest legacies of Babylonian mathematics.
Quadratic equations involve things where the unknown quantity you're trying to identify is multiplied by itself. We call this squaring because it gives the area of a square. And it's in the context of calculating the area of land that these quadratic equations naturally arise.
Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3x3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64.
So the size of the square are 8 units. The problem solver knows that they've added 3 to this side. So the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history. In modern mathematics, I would use the symbolic language of algebra to solve this problem. The amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics. The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players. The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs to little bits of board games found in schools to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
Now's my chance. I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
So 6, and I need to move something, so...
But it wasn't as easy as I thought.
What the hell is that?
Yeah, this is
1, this is 2.
Chance. I hadn't played
hard work.
Now's my chance. I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
So 6, and I need to move something, so...
But it wasn't as easy as I thought.
What the hell is that?
Yeah, this is
1, this is 2. Now you are in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these. You're gonna
I've just got to... Oh, gosh.
Exactly. There you go.
You seem to be...
3 and 4. So...
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there. All right, good game.
Here are 5 facts every investor should know about the Nasdaq 100. The Nasdaq 100 comprises the 100 largest
The Babylonians are recognized as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322, and
These numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem, and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of three numbers which fulfill Pythagoras' theorem.
It's not a systematic exploration of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
Power began to wane,